Hello and welcome to Forensic Toxicology Introduction. This course is an online course that's the Forensic Survey course, and we're going to be discussing forensic toxicology. I know the syllabus says trace evidence as well, but we're going to stick with forensic toxicology, and I may touch on trace evidence on occasion. My name is Dr. Jared Wagner, and I'll be talking to you a little bit about my background as we're going through the different materials. So, first of all, what is forensic science and what is forensic toxicology? Forensic science is the application of science to the courtroom. So that can take a lot of different forms. We have experts in forensic DNA, we have experts in forensic toxicology, criminalistics, crime scene, different things, but they're all applications of science to courtroom problems. Forensic toxicology is looking at toxicology as a whole and then taking those toxicological applications, which is the study of poisons and the study of drugs. Pharmacology is technically the study of drugs, but toxicology really encompasses drugs and poisons, and we're looking at negative effects that those might have on the body. So, my background, I actually have a bachelor's in chemistry and a bachelor's in biology from UC Irvine and a PhD in environmental toxicology. At the time when I earned my degree, I was really interested I wanted to work in law enforcement. I was interested in forensic sciences, and I'd done some internships as an undergraduate. And at the time, my advisors in the crime lab, my mentor said that I really should pursue a PhD if I wanted to be in the lab, because that was really the direction that laboratories were going. We're starting to see this a little bit from some of the outcomes of the scientific working groups and also the OSAC committees that are starting to establish standards. But either way, that's why I studied what I did. I was a reserve police officer for a little while when I started. I was a graduate student, and I went through the Sheriff's Academy, and then I got hired by Irvine Police Department, and I actually worked patrol in a car. I would pull over people for DUI, issue field sobriety tests, sometimes in Spanish, and work just general patrol functions as a volunteer. And it was it was a great experience, and I had to learn the penal code very well. So it was good. As I mentioned, I did an internship with the Orange County Sheriff's Department and also with the FBI. When I got done with school, forensics, I got hired as a forensic scientist in the Orange County Sheriff's Coroner's Office in Orange County, which is Santa Ana, California. From there, I was there a couple of years, and then I went to a tenure track assistant professor position at Fresno State, or California State University, Fresno, and then got an opportunity to work in the hazmat response unit of the FBI lab, which I really enjoyed. And then I came here to OSU, which I really enjoy. So I'm an associate professor here, and my main focus is forensic toxicology, but I also do trace explosives work and have some specialization in clan labs. So now we'll talk a little bit about forensic science. As I mentioned, forensic means it's really public. So sometimes you'll hear people discuss forensics and it's like a speech class or something. It's a public forum. And there are forensics teams that are like debate. But forensics, when we're talking about it, it's related to the court, and forensic science is applying scientific knowledge to legal problems. So there's lots of different forensic specializations. I talked about a few of them. You don't have to memorize this list. There's lots of different areas of science where there are specific applications. So tonight we're talking about the one on the lower right, toxicology. We have forensic chemistry. That's more controlled substances and some of the trace chemistry that I do. We have forensic anthropology. I don't really do that. That's all about identifying remains from bones and such. Anyway, there's lots of different disciplines that are represented where someone might specialize to apply to court. Here's some of the basic sciences that you might run into or need to know as you proceed with a career in forensic sciences or studying forensic sciences. And, in toxicology, we use these. We use physiology, we use pharmacology, we use pathology, we use molecular biology. We have to understand these things in order to do our jobs. So these are just some of the basic sciences that we run into. So one of the questions that comes up is what are the roles in forensic science? Because you see things on TV, you see maybe a person on TV that's a sworn uh, law enforcement employee, but they're actually a forensic scientist as well, and that's actually fairly rare now. Most of the time, we're going to have a forensic scientist, that, or a criminalist. Sometimes we call them criminalists. They practice criminalistics, and they're going to be at a local lab, a state lab, or a federal lab. In Oklahoma, an example of a local lab would be the Tulsa Police Department. The state lab would be the Oklahoma State Bureau of Investigation, or OSBI lab. The federal lab, DEA lab, they have, I think, 9 accredited labs. ATF has 3 or 4 accredited labs, and then the FBI has 1 accredited lab. So these are examples of, these are places you could practice. But maybe you don't want to work in a crime lab all the time, but you want to use forensic science. First responders, police officers, sheriff, deputies, they might use them. We actually have investigators for the coroner's or medical examiner's office. We have a track called Death Scene Investigation that's focused towards that. And they use forensic science in what they're doing. Also, district attorney's office have investigators that would use it. And then federal agents, whether it's FBI, DEA, ATF, EPA, DHS. DHS is now, we're seeing a lot of Homeland Security investigations stuff pop up on the news, and so it's kind of growing a bit. So what actually happens in a crime, and how is forensic science even involved in the criminal justice system? So first you have some sort of a crime or suspected crime committed. So it might be fraud, burglary, rape, murder, and someone's going to respond to that event, and they're going to start documenting what occurred and investigating it. It could be local police, sheriff, district attorney's office, could be state or federal. Sometimes specialized personnel might respond depending on what sort of crime it was. Based on their finding, they prepare a report that's provided to the district attorney or U.S. attorney, and they'll decide whether to charge somebody with a crime if they know, 1, that a crime occurred, and 2, that they have someone available to charge. And if this happens, this goes to court, evidence is presented, and that both prosecution and defense have a chance to present evidence and also interpret the evidence and give their version to the jury. Now, the jury is going to be a jury of peers, 12 peers, that are not professional necessarily. They wouldn't have any specialized training in forensic science, and that can be challenging, because you've got to teach them as a forensic scientist what you're trying to get across about whatever it was that you found. Why does that include the suspect, or why does it not include the suspect? So after the jury renders a verdict, then there will be a sentencing period. These are some of the disciplines that are common to most crime laboratories. We have latent print examinations, question document examinations. Latent prints are hidden fingerprints. Question documents, and these are in the Tulsa Police Department lab downstairs. Question documents is a signature real? Is it fraud? Firearms and tool marks, other impression evidence. Crime scene response. Not everyone responds to crime scenes anymore. It just sort of depends on the department. Energetic materials. You might have someone doing explosives and fire debris. Sometimes that's part of trace, but not always. Postmortem toxicology is separate than human performance testing. Postmortem would be for the Office of Chief Medical Examiner, where you get toxicology specimens and you're trying to interpret how those specimens, how the toxins that are present were maybe involved in the cause and manner of death. With human performance testing, you're really focusing on, we call it antemortem testing, so before death or while they're living. And we're worried about things like DUI there, where we're trying to determine if someone was driving impaired. Forensic biology and molecular biochemistry, this would be forensic DNA analysis or serology. Typically we use DNA today, but serology, we're finding all kinds of new techniques, but this is all focused towards identification. Trace evidence is typically microscopic examinations. It can be instrumental, like is done in my lab, but often when you think of trace, you're focusing on fibers and things like that. And then controlled substances examinations, those are units that are dedicated to identifying the different kinds of controlled substances out there, and if they are present and if they're legal or not. So that's what that is. In the lab, what do they look at? So there's physical evidence. The trace will look at hairs, fibers, soil, explosive residues, gunshot residues. Latent prints are just looking for hidden fingerprints. Controlled substances is looking at bulk powders and liquids that might contain a controlled substance. Biological evidence is going to be blood, urine, semen, tissues, wipes. There's different things that they're trying to get DNA off of. Documents are going to be the physical evidence for handwriting analysis. Photographic evidence, the crime scene, trauma, pathology, you're going to want to document that. You're going to create physical evidence with your documentation. And then sometimes there's tapes of 911 calls or things like that. Computer can provide evidence of a crime. Obviously, it's actually a very specialized discipline, digital evidence, but it is something that we have to be aware of. So responding agencies will respond and collect the evidence, and they'll seal it for examination. There are some situations now where it's done on site, but most of the time it is done at least for court purposes, it's done in the crime lab or later. And although you might have preliminary examination done, so we have drug kits or narcotics identification kits that officers can use, and it's a presumptive test. DUI breath tests are not preserved, so there's no additional evidence collection. That is often done in the field if someone chooses a breath test. A forensic scientist might collect evidence, but they don't have to. But they might evaluate evidence, and then they're going to generate a report or a factual finding, and then they're going to go to court to interpret those findings. Physical evidence from a corpse, this would be post-mortem, someone has been killed. It's not always a medical examiner that's doing the analysis. I know some of you guys and gals have probably seen TV shows where a pathologist is walking you through everything. They have these subdisciplines where they're getting the evidence to other people. So toxicological analysis, we're going to be talking about forensic tox tonight. They analyze tissues and fluids that were associated with the body. There might be pathology on the tissue sections to look at on the microscopic level, was there illness indicated. From a public health standpoint, sometimes they're looking for viruses or bacterial infections. The bodies might be examined for trace and GSR, so gunshot residue. And we also have identification where we're going to try and identify the body based on DNA and fingerprints. A criminalist or forensic scientist, they're going to be testifying about their chain of evidence. And I don't want to step too much on Tara Bryan's lecture, so but just generally, a criminalist is going to go in and they're going to testify about where did I collect the evidence from, where did it go while I had it in my possession, what did I do with that evidence, and what are the results of my examinations. And sometimes those sometimes just can provide the facts that I analyzed it and this is my conclusion. Sometimes they're offering an opinion. They're an expert witness, and they're asked to present their opinion. It just sort of depends. And then once that opinion is presented, other experts in that field can disagree, and that often happens. So we have people that are forensic toxicologists. They won't all agree on an answer. Sometimes they do, but you have to have an advocate for the prosecution and for the defense. So typically when a criminalist that works in a public lab presents their evidence, you can expect it'll be challenged by someone on the defense side. So the prosecution and the defense present the cases to the jury. The jury has to weigh the arguments, determine guilt or innocence. So somewhere in that process, we have to have a way to maintain integrity. So how do we do that? So how do we know that a criminalist is not a criminal? How do we know a first responder is not someone that is breaking the law or doing something illegal? And so one of the things that we do in crime labs is that we actually do background checks and polygraphs. This with FBI, multiple polygraphs. We also have educational and training standards. I believe Tulsa Police Department requires a bachelor's degree to work for the agency. You can get individual accreditations. Um, the American Board of Criminalistics has an accreditation. I don't have that one. American Board of Forensic Toxicology, I do have that one. It used to be called Diplomate, but now it's called Fellow for my level. And the laboratory can be accredited. So if you look at the lab downstairs, they're going to talk about Tara's lab. They are an ASCLD lab accredited laboratory, and that's an international or an ISO accreditation, and it's actually done by the American Society of Crime Laboratory Directors Laboratory Accreditation Board. But that's one of the ways that we maintain integrity, by having the lab subject to review and audit. So for forensic scientists, if that's the career you have in mind, you really need to be looking at a bachelor's degree in a relevant discipline. Chemistry, biology, or related would be good. You need coursework in quantitative chemistry, typically. DNA, you probably should have coursework in molecular biology and biochemistry, and maybe PopGen or population genetics. Statistics is valuable for everybody, regardless, and we're seeing more of an emphasis now on statistics in forensic science interpretation. So it's definitely something you want to pay attention to. Other training for forensic science, we can do research in various sciences. We can do internships in crime laboratories. You guys are taking a class in an MSFS program. There are other degree programs you could be pursuing, chemistry, molecular biology. Eventually, you can get a PhD in forensic science. Here, we don't have a PhD in forensic science. There's a couple of places offering them now, Florida International and also Sam Houston State. They're challenging to do a PhD in it. We have considered it. I do have students in my lab that are earning PhDs, and we've had other students earn them in our department, and it's usually through either biomedical sciences or veterinary biomedical sciences. But you don't have to pick a forensic science specific degree program to earn a relevant PhD. So one of the things that we found, the NIS report was released in February of 2009, and it just calls for more labs to be accredited, more certification of individuals, more research into the meaning of the findings, more education about how to do forensic science, more training about how to apply your knowledge in the field, more funding to support the training and education, and also new structures. It recommended some new innovative programs for funding research in forensic sciences. This was in 2009. Last year, and actually 2 weeks ago, we just published. I was on a National Academy of Sciences Commission and a committee that reviewed the progress of the National Institute of Justice, that's part of the DOJ that funds research, and we looked at their progress since the 2009 report, and they've really come a long way towards building up quality and supporting research in forensic science. So anyway, that might be something if you guys are interested to look up that report. But that really is the future. High quality work where we know what the work means. So you guys are familiar with this. Probably this is our building. The first floor is the Center for Health Sciences, Forensics and Biomedical Research building is the Tulsa Police Department Crime Lab. The first floor is the property room. The second floor is the crime lab. And then Forensic Sciences is located on the third floor. It's great to have us co-located. We also have the Office of Chief Medical Examiner, the OCME here on site, and they don't do toxicology here, but they do autopsies. And then if they need toxicology done, it's sent to Oklahoma City. So, and we do have students that do internships. We've had them at OSBI and also at OCME. So, forensic toxicology. What is it? What's the history of it? What are some issues associated with legal proceedings? What's a toxicologist's role? And what specimens they look at? We're going to look at how we do analysis and what happens, how do materials get distributed and excreted from the body. That's called ADME, or absorption, distribution, metabolism, and excretion. Then we'll talk about a couple of case studies. So just to be realistic here, If you look at this quote from Arnold Lehman in 1955, this is referencing general toxicology, not forensic toxicology, but he said, "You too can be a toxicologist in 2 easy lessons, each of 10 years. So in this course, you get 2 lectures on forensic tox. So we're not expecting you to become toxicologists as a result of survey. We're just trying to familiarize you with the subject matter. So toxicology is the study of poisons, and forensics refers to the legal system, which we talked about briefly earlier. Forensic toxicology is the application of toxicology to legal matters. Some of the history, before Christ here, this is a long time ago. We found papyrus that reference hemlock, aconite, opium, lead, copper, and antimony. Hippocrates in 400 BC added a discussion of bioavailability and overdosage. Theophrastus from 370 to 286 referenced poisonous plants. The Lex Cornelia in 82 BC was a law against poisoning people. And Dioscorides in 40 AD classified poisons according to plant, animal, and mineral. There were professional poisoners in the Middle Ages that sold their services to royalty and also people looking to kill other people. And arsenic gained the nickname inheritance powder at that time. Philippus Areolus Theophrastus Bombastus von Hohenheim is known as Paracelsus. He lived from 1493 to 1541, and he said something pretty unique. He came up with basically the dose-response curve. He said, all substances are poison. There is none which is not a poison. The right dose differentiates a poison from a remedy. And if you were saying, no, that's not true, water's not a poison, actually, if you drink too much water, you can get what's called hypokalemia, where you don't have enough ions, and you can have basically it's almost like having a heart attack, but you die. So anything can be a poison in the right dose. So Paracelsus, and actually at our SOF meeting in last year, the Society of Forensic Toxicology meeting in Grand Rapids, we made our own brew, and it was called The Dose Makes the Poison Ale. But then they didn't like the word poison on the front of the bottle, so we changed the name of our ale to Paracelsus Ale. He focused on the chemical entity as a toxicant. And he said that he actually established that you could experiment and determine the response to chemicals. He distinguished between therapeutic doses and toxic doses. Therapeutic properties and toxic properties, and then noticed that sometimes, depending on what dose you gave, you got therapeutic results versus toxic results. And the degree of specificity and the therapeutic or toxic effects can be determined. So this was really important for toxicology in general. In 1775, this is sort of moving up a long way, Scheele was a Swedish chemist, and he determined that he made an analytical method to identify arsenic. The Marsh test, if you've heard of this test, he applied a test to tissues with acid and digested them. And this was 1836. Orfila, from 1787 to 1853, he was a Spanish physician in the French court, and he was the first toxicologist to use autopsy and chemical analysis to prove poisoning in a courtroom trial. Stoss, in 1850, extracted nicotine from a murder victim, and that's we get the Stoss-Otto method, which was the first alkaloid screen, which is a common screen we still do today, a basic drug screen. Rudolph Whithouse from Cornell in 1911 edited the first standard forensic textbook. So more recently, in 1918, City of New York, Dr. Alexander Gettler was the first medical examiner, really the first forensic toxicologist. And in 1949, the American Academy of Forensic Sciences was formed. 1975, the American Board of Forensic Toxicology was formed. These are 2 references that you can use. I'm hoping they're still valid, but there's some really good stories about toxicologists in history, and they sort of bring some of this history that we've been talking about to life. So, in modern forensic toxicology, we have several different disciplines or several different divisions. The first is postmortem toxicology. That's going to be after you're dead. So it's the analysis of specimens to determine analyte characteristics in dead people to aid in determining the cause and manner of death. Human performance testing is sort of the antemortem testing I referred to earlier. And in that case, we're going to analyze specimens to determine if someone's driving impaired or has a health and safety violation or a major crime where they're impaired at the time of the act. And in forensic drug testing, it's a very controlled field. It's NLCP, National Laboratory Certification Program, and this covers the analysis of specimen to determine if people that are working have been using drugs. And this is done to, it's a requirement for some federal funding, and also it's to make sure that people, if they're operating forklifts or heavy machinery, that they're not doing that while impaired. In order to present evidence in court regarding a matter, we have certain legal requirements. So a qualified witness, we actually have to determine if someone's going to be an expert. So we do something called voir dire, where we ask questions of the witness and determine if they are in fact an expert. And then the evidence itself has to be presented. It has to be related to the trial, and it's got to be admissible. And there are lots of federal rules and local rules of evidence. You've probably heard of Daubert and Kumho and some other cases that have governed the admissibility of evidence. One of the other questions we have to ask is the chain of custody complete, and has the evidence integrity been maintained through the process? And that's important. So, if you were to say, have a power outage in your lab and not have the evidence wasn't refrigerated when it was supposed to be, could that have hurt the integrity of the evidence? But those types of things are things that we want to control for in a legal setting. I mentioned accreditation and certification. These are the things that are available for toxicology. We have ASCLD ISO, which Tara's lab downstairs is certified through ASCLD ISO. The ABFT provides a certification. SAMHSA, the NLCP I mentioned already. Society of Forensic Toxicology offered guidelines, but they do not provide accreditation, and the College of American Pathologists will accredit laboratories. So as far as proficiency tests, these are tests that we perform to verify that we're performing our work properly. So there's a couple of different providers. The College of American Pathologists can provide them. The FAA can provide them. California Association of Toxicologists will provide them. And then if you actually want to get your personnel certified versus your laboratory. So these things on the left are really to certify your laboratory through laboratory accreditation. Personal certification is we're going to certify the individual. The Forensic Toxicologist Certification Board does not exist anymore. It was absorbed by ABFT, so that's where that whole change came from a diplomat to a fellow. The American Association for Clinical Chemistry is one. NRCC is not on here. National Registry of Certified Chemists, American Board of Toxicology, American Board of Criminalistics, Toxicology Specialty. So these are some of the accreditations that are available to toxicologists. So what's a toxicologist's role? Basically, you're going to perform analytical chemistry in the laboratory to determine if drugs or poisons were involved. And you notice I use the term xenobiotic. Xenobiotic is anything that's foreign to the body. So we're trying to figure out if something was ingested or injected or they were exposed to something that has in any way related to the death or the behavior. So we try and identify drugs or poisons that are consistent with the behavior that they're exhibiting. And we try and choose the right tools to screen for. So, for instance, if someone acted very stimulated and they were acting, they had high blood pressure and dilated pupils, you would want to screen for a stimulant, not for an opiate. Opiates are going to cause constricted pupils and very respiratory depression. So you want to carry out the right analytical technique to determine the presence or absence of a drug or poison. Often, a lab will have a set screening system that they use, so every sample gets tested for certain drugs, but it's really dependent on the lab. One of the things that the toxicologists are asked to do is to identify how the drug was administered. This may be possible, it may not be. Sometimes they can do this based on the ratio of different analytes. It's challenging. Sometimes they're asked to determine or estimate how much was administered and when it was administered, and they're asked, are the findings consistent with the purported behavior or death? These are all goals that we have to interpret these findings, but it's very difficult to know if someone took a lot a long time ago or a little bit recently. So it's very difficult to interpret the level that we detect in these assays and know, okay, that means that they took 2 lines of cocaine yesterday. It's going to be very difficult to do. Analytical chemistry and knowledge of analytical chemistry principles to identify unknown chemicals and how much is there, that's really important for the practice of forensic toxicology. That's great to get an answer, but in order to move beyond that answer, you have to be able to interpret that finding and apply it to relevant organisms. So you really need to understand both analytical chemistry and toxicology. In terms of specimen types, we have lots of different specimen types available, but we definitely have more available for postmortem than we do for antemortem, because people don't generally want to let people poke a needle in their eye to get vitreous humor while they're awake and alive. So postmortem samples, we can get heart blood, peripheral blood, vitreous humor, bile, urine, stomach contents, brain, and liver. Antemortem studies, blood, urine, breath, and saliva or oral fluids are all used. Forensic drug testing, urine, sweat, and hair. They're actually coming out with a guideline for oral fluid as well, or saliva. So biological specimens are actually complex mixtures. So we'll have cells, proteins, lipids, water, dissolved ions. Sometimes they're putrefied, so they'll have chemicals from biological degradation. So there'll be sometimes amines, that sort of fishy smell, and then putrefied body smell is from these chemicals that are being formed as the body's broken down. And sometimes we call those cases decomps, and some of those cases will give false positives for amphetamines. And hair, some of the hair levels can be from environmental exposure. One of the things that you see here on this chart is I just tried to, if we're just analyzing whole blood, that's there on the left. If we centrifuge it before allowing it to clot, we'll get the red blood cells on the bottom. We'll get a buffy coat with the white blood cells, and then we'll get the plasma, about 55% of the volume of the blood on the top. So if you say, what's the level in plasma? That blood sample has been centrifuged, and the plasma is what's on the top. If you hear about serum, what they're doing is they let the blood clot, and then they spin it down, and the supernatant is serum. And it's different from plasma because it doesn't contain fibrinogen. So that's where the samples come from. Sample preparation or specimen preparation. There's some simple prep methods where you can just dilute the sample down. You can sort of get rid of interference by diluting them out. You can crash out proteins or precipitate proteins with a solvent, spin it down so the proteins build up on the bottom, and then you can get your specimen from the top. You can do headspace analysis, and this is what you might do in the case of blood alcohol analysis, where it's a sealed vial, and there is a equilibrium between the blood and the headspace, and basically the ethanol is in the blood, and it's also in the air above the tube. It's called the headspace, and we go down and we sample the air and get the level of alcohol in the blood. We can use SPME analysis. It's pretty simple. It's solid phase microextraction. It is a little tricky. You really should have an auto sampler to do this because it's easy to ruin the fibers on accident when you're using this technique. So more complicated techniques, which are often required, solid phase extraction and also liquid-liquid extraction. So liquid-liquid extraction is sort of what I began my career doing. Uses some of the Stoss-Otto methodology and things, and solid phase extraction is a little bit different. So we're going to go through how solid phase works here in a little bit, and we'll talk about that as part of the class. So first of all, what are the different things that we're looking to identify here? It gets a little bit tricky in forensic toxicology because we say we want to find acidic drugs or we want to find basic drugs, and we get confused about what that means. Usually, acidic drugs are acids. They have a carboxylic acid functional group on it. So if you look in this diagram, you see on the left, you see this hydroxyl. This is a completed carboxylic acid functional group with an H on it. The pH is below the pKa. Therefore, there's a lot of hydrogen ions in solutions or protons in solutions, and they form COOH. But this is not a positively charged compound. This is actually neutral. And above the pH, that's the pKa, we find it's in the form of the carboxylic acid anion, or COO minus. The H has been removed because you're getting more basic, and it is now negatively charged. Neutrals are things like fats, and there's certain chemicals that don't have any ionizable functional groups on them. So these are going to go into an organic most of the time from the blood. Basics. Basic chemicals, typically in toxicology, we're talking about amines. So you can see that this is an example of a primary amine. And as the pH gets lower, you have more protons in solution, and it'll actually convert from the neutral NH2 below the pKa, it becomes NH3+. So if you go from low pH to high pH, it'll go from a protonated amine to a neutral amine. So this is really important because what we're going to do is we're going to use these characteristics to selectively determine where we're actually going to analyze for the acid drugs, the basic drugs, or the neutrals. And we're going to be able to do that through different extraction techniques. Sometimes we look for metals, and that can be pretty challenging. But we're going to adjust the pH so acids and bases are neutral, and then extract them. Or if we wanted, anyway, we'll do it for bases and we'll do it for acids. And it looks a little bit different in each case, but I'll talk a little bit more about it. Here's some of the ionization constants of common drugs. You're like, well, why do I need to know that? Well, looking in the case of, say, methamphetamine, the pKa is about 10. When we do an extraction and we want to extract methamphetamine, if the pH is 8 or so, which is what it's going to be in blood, we're going to have methamphetamine. It's going to be protonated. It's going to be NH3+, and it's going to be water soluble because it's got a charge on it. But if we change the pH of that blood to, say, 11, most of that methamphetamine is going to go to the NH2 form, and it will actually be neutral. So it will come into the organic phase. So that's an example of extracting a basic drug. We change the pH to basic and then pull that drug out. And let's see if I can find an example. On the left here, aspirin, that's a acetylsalicylic acid. It's got a pKa of 3.5. So if we take at pH of 7, it's going to be negatively charged. And as we lower the pH below the pKa of 3.5, we take it down to about 2 with an acid. That aspirin becomes neutral. So that will then extract into the organic. And that's by knowing the pKa's of the different drugs, that's how we are able to selectively extract them. This is from Casret and Duels. This is just showing a differential solvent extraction or a liquid-liquid extraction and how it's done. And it basically is the process that I talked to you about. If you acidify it, you can test for residues. If you acidify it and then do a organic extraction, you'll get the neutrals and acids in it. But if you take that organic and then you re-extract it with water, you can pull your drugs back into the water and then leave your fats and stuff behind. So we usually do a double extraction because we want to get rid of a lot of the neutrals. Anyway, we're going to do that here. Same thing. We're going to extract the organic, basically change the pH and extract with an organic, and then we can analyze for organic, for acidic drugs, or we can analyze for basic drugs. And the techniques that we use, all we're trying to do is basically take a drug that wants to be in your blood with everything else that you have in your system, and we're going to try and selectively pull it out and put it into a clean solvent that we can analyze by, say, gas chromatography, mass spectrometry, or LCMS. So that's what we do in forensic toxicology. Solid phase microextraction. I described this to you a little bit. It basically has like column material, which is what you use for chromatography, and it's on a needle. You can place that needle in the headspace and it'll equilibrate, and then you take the needle out and you inject it in the GC or LC. So this is what that looks like. We can place the septum on the sample container. We put our spemy fiber in, expose it, retract our spemy fiber and pull this out. Then you put this in the septum of your GC and expose your needle in the GC and then inject it. So it's a kind of unique, it's a unique way to analyze samples. In solid phase extraction, our sorbent is going to actually trap the analyte of interest, and then we're going to wash away other materials we don't want to see, and then we're going to elute what we want to find. So here's an example of a diagram of solid phase extraction. This is out of the Sapelco or Sigma catalog. So you got to pick the right solid phase extraction tube. You condition it so that you activate it and your drugs will stay on it. Then you add your samples, and you see that there's a mixture of triangles and diamonds and squares here. You're going to add those on, and some of those are going to leave, and then you're going to wash it off so that all you have left is your analyte, and then you elute your compounds of interest in the end so that you have a nice clean sample to put on your LCMS or GCMS. So we can do a couple of different types of analyses in toxicology. We can do qualitative examinations where all we're doing is saying it's there or it isn't there. And we have to know what the cutoff is. We have to know what our limited detection is. But the qualitative examination is just qualitative. It's not quantitative. It doesn't say how much. A quantitative exam says how much is present. And this is a lot of the work that's done in forensic toxicology to determine quantitating how much drug is there. We'll also do a screening test, which might be a presumptive test, which differs from a confirmatory test in that a screening test is usually, it's a little bit more general. It might have a little higher false positive rate, but it will have a low false negative rate. And you can see false positives, it means I thought I detected what I was looking for, but it wasn't really there. So like if it gave you, you did a decomp case with a screening test like ELISA, and it came out as being positive for the decomp, but then you did an analysis and there's no methamphetamine or amphetamine present, that would be a false positive. False negatives, I thought none of the stuff I was looking for was detected, but it was actually there. So in that case, you might do a study and find, wow, there's what I was looking for is not, it's not here, but really the person has a bunch of meth or whatever on board. In a confirmatory test, it's meant to be a complementary technique. So you can do a screening technique with one technique, like ELISA, an antibody-based technique, and then a confirmatory test is going to be more specific. It's going to be a different methodology. You don't want to use the same methodology for both because you want the techniques to complement each other. And that that's very that's very important. Sometimes a confirmatory test will identify the amount of material present, but it just sort of depends if it's quantitative or qualitative. So immunoassay or antibody-based testing, we'll have radioimmunoassays, emits, ELISAs. We can have colorimetric testing. These are all screening tests that just tells me something's there. TLC, thin layer chromatography. You know, some people would say this is quantitative. It can be. It's not exactly. I would not going to have a very high confidence in the number value if you try to quantitate based on this. And if you've ever done TLC, you understand why I'm saying this. It just makes a blob that goes down with chromatography, and you can identify things by ratio of fronts. But you can get an idea of how much is there, but really it's not made to be quantitative. So confirmatory method, UV-Vis, UV-Vis spectrophotometry. We use the UV, ultraviolet, or visible range of light and we can identify the presence of carbon monoxide or cyanide. Sometimes other drugs will have hyphenated techniques. What we mean by that is chromatography with some sort of detector. So when I say GCMS, that's gas chromatography with mass spec. GCMS-MS, that's gas chromatography with tandem mass spectrometry. LC, LCMS-MS, LCMS, these are all liquid chromatography with mass spec. These are going to be confirmatory techniques, and again, they can be qualitative or quantitative depending on what you're looking at. So I haven't gone into a big explanation of how mass specs works, how mass spectrometers work. And basically what mass specs are is they just identify what actual material is present by looking at fragmentation spectra of it. And so it's kind of like tuning in a radio. You know, the station's at 103.1, so you're going to turn to 103.1 to see it. And if the radio station's on, you'll hear it. It's kind of how mass specs work most of the time. So let's say you've got a mass spec or you got a UV-Vis. You've got some way that you're going to be able to see your compound. Now the question is, how do you use that in a way that is going to allow you to identify how much is present? So there's a couple of different ways to quantitate. One of the methods that we like to use, there's internal standard methods and there's external standard method. But generally, in forensic toxicology, we use internal standard calibration methods. So we pick a chemical that's going to behave like the analyte, and we're going to add it to everything. So for an alcohol analysis, it might be N-propanol. And then we're going to do an analysis, and we're going to get a ratio of our analyte to that internal standard that was the same. And then we're going to plot that versus concentration for a standard curve. And then we get a best fit line, and we use it to calculate our unknown. So this is kind of tough to explain, but I came up with a marble example. So Billy and Sarah have a giant bag of multicolored marbles. They don't know how many it contains. And they decide they're going to try and do it, try and determine how much they have without actually counting each marble. So they count out sets of 100, 50, and 25 marbles and put them in separate bags. There's no red marbles in any of the bags. And then they add 10 red marbles to each of the bags they have prepared. And then they add 10 red marbles to another bag containing no other marbles. So they also, that would be a blank. Then they add 10 marbles to the bag containing the unknown amount of marbles, and then they mix all the bags thoroughly. So they pour out a small amount of each bag through a funnel into a jar for counting, and they do each bag separately, and the following are the results. So with 0 marbles, they got no green and 2 red. Green to red ratio was 0. For 25 marbles, they got 15 green and 6 red, which is a ratio of 2.5. For the bag of 50 marbles, they got 15 green and 3 red, which is a ratio of 5. And for the bag with 100 marbles, they got a ratio of 10, with 20 green and 2 red. In their unknown bag, they got an answer of, they got a ratio of 20. So how many marbles should they have? In order to figure that out, or do they have, we actually have to plot the results in a graph and figure out how many they have, and we have to add a trend line to it. And if you can do this in Excel, it's kind of fun. Well, not really, but you can do it. And you get this line. And then you just go up to the answer of 20 and you can see that they have 200 marbles in the unknown bag. Now here's the thing. This is fine for a little example to try and explain to you how we use the ratio of analyte to internal standard to get a concentration. But we never want our unknown to be out here and not bracketed by internal standard. We want our unknown to fit somewhere along the curve here. So if we wanted to have a value of 20, we would need to do another bag that was at 30. And then you would have a nice number of standards and it would be bracketed by your standards. So the result should be in the linear range of your method, and you really want it bracketed by 2 calibrators. And you have to make sure that the quantitation meets acceptable criteria and that your lower limit of quantitation is accurate. Your controls have to be within a certain percentage of known values, and you can have only a certain amount of variation. Typically, on a typical calibration curve, along the curve, it's going to be 15% accuracy and 15% precision. And at the cutoff, or at the very lowest level, it's going to be 20% for both. But it really depends on the lab, and it depends on the method, and it depends what you validated. So in toxicology, we'll run high, medium, and cutoff, and blank calibrators before our samples, and then after in reverse order, and we'll sometimes run quality control samples in between to show that everything was working. And the blanks, we run blanks, so we want to see if they're telling us that there's analyte there when there's not. We're trying to detect carryover. But we also validate the methods to make sure that typically there isn't carryover, and we have to make sure that when we give an answer, it's a true answer. We also have to make sure our standards are good. There's a lot of work that goes into making sure a forensic toxicology method is valid, and we have to document those steps in very large reports. And that's a part of the accreditation process too, is they review your method and your validation. So I told you I was going to talk to you a little bit about what we call ADME, which is absorption, distribution, metabolism, and excretion. Absorption is the path of the drug or poison in the body and the rate. So absorption talks about how rapidly something's absorbed and how it's absorbed. Distribution describes where the drug goes when it goes in the body after it's absorbed. Metabolism talks about the process of biotransforming the drug to get it out of the body and how fast that occurs. And excretion describes which way is that leaving the body. So ingestion routes and absorption, routes of absorption include ingestion, which is eating. You can inhale it, so if you think of cigarettes. Dermal, the patch, nicotine patch or fentanyl patch. Injection, we can have an injection. So that's absorption. Distribution, it really depends on hydrophilic or hydrophobic nature of the drugs, where they're distributed in the body. Hydrophilic, I already mentioned to you that when things are ionized, they want to be in water, which blood's a lot of water. So if it's a hydrophilic compound, it's going to be distributed well in blood. But if it's hydrophobic, it doesn't want to travel in the blood. It wants to travel in lipids, or it wants to get stuck in tissues with a lot of lipids and fats. The volume of distribution is this theoretical concept we've come up with, which basically describes the volume in which an amount of drug would need to be uniformly dissolved in order to produce the observed blood concentration. So in distribution, we're really looking at, we can have multiple compartment models where the drug goes to more than one compartment, or it can only be one compartment. It just depends what your blood level becomes once you absorb a drug. And so it's a challenging concept, but you get more of that if you take the forensic toxicology course or the advanced forensic toxicology course. Metabolism is when we want to get rid of a drug, and really, you guys maybe are familiar with ethanol. We metabolize ethanol, and There's a certain rate. We metabolize about 0.015 an hour. There's different rates. But typically with any analyte, we start with oxidation and then we go to conjugation. So that first we break it down and then we'll conjugate it with a sugar. So we make like a glucuronide, or sometimes with a sulfate group, and we make ethyl sulfate and things. So these are examples of metabolism. If you look here at this figure, we have phase 1. These are all phase 1 enzymatic reactions to break down foreign compounds. You see alcohol dehydrogenase, aldehyde dehydrogenase, and we have our carboxyl esterases, where we perform hydrolysis. And then after we've broken them down in phase 1, we'll go to phase 2, where conjugation. So we'll add sulfonal compounds to them, or sulfate compounds. We can add glutathione. We'll add glucose. And basically what we're trying to do is make the compound or the drug more water soluble, so it's more easy to excrete. So when we go to excretion, there's a few places we can get rid of it. One is the breath. So that's why we measure breath alcohol. Your body is blowing off alcohol through your breath. It's equilibrating between your blood and your lungs, and we can get the ratio of breath to blood and then determine what your blood alcohol is from your breath. Fecal matter, it could be that it goes into the bile and it goes into your fecal matter. Urine, obviously that's the kidneys are a major excretion pathway. The liver does a lot of metabolism and it can put things into the bile. Sweat, we can actually sweat out. If you notice someone that smells like beer the day after drinking, sometimes they're still sweating out those toxins and poisons and alcohol from their body the next day. So the half-life, or tau, of a compound is the amount of time required for the amount of the analyte in the body to be halved. So oftentimes you'll hear, if it's a really long half-life, it just means that the compound is very stable in the system. It might have a larger effect because of that. It sort of depends on what the analyte is and what its effect is to begin with. This is an example showing you the different routes of absorption and where things go. And you can kind of see this recirculation that's taking place right here. This is, it's interesting, you ingest it into the GI tract. It then is absorbed in the portal flow to the liver. And then it can go back into the blood, and it can flow around the body. It can also go into the bile and then back to the GI tract. There's something called first pass metabolism, where if you ingest it, it has to go through the liver, versus IV goes straight into the blood. Or inhalation, if you look at inhalation, it goes into the lung first, and then it goes straight into the blood, but it doesn't go through like a portal circulation the way that things do when they're ingested. So this will actually result. This is why drugs, depending on how you absorb them, you'll have different effects of those drugs. So, and right now we're dealing with cannabis. A lot of people are eating marijuana edibles, and that absorption is taking place slowly. And sometimes it turns out that that's more toxic than if it was inhaled. It sort of depends. We're having a lot of issues trying to get our hands really understand how those marijuana edibles are going to result, what the outcome is going to be for public health. Because, obviously you guys may be familiar with them in the news, but we've had a lot of people commit suicide and just behave very erratically after indulging in marijuana edibles. So it's something to be aware of. So ADME is pharmacokinetics. Pharmacokinetics is the process that identifies the amount that affects the amount of xenobiotic at its site of action. Pharmacodynamics is what that drug or chemical is doing at the target that gives its physiological effect. So ADME gives how much is there. Pharmacodynamics is going to tell you what happens as a result of that. So Pharmacokinetics is, we dose you with the drug. There's the drug concentration in systemic circulation after absorption. It's distributed to drugs in the tissues. It's eliminated and it's metabolized and excreted. That's pharmacokinetics. The drug concentration at the site of action and a pharmacological effect and the clinical response of either toxicity or efficacy, that is pharmacodynamics. And that is really, really important for forensic toxicology. There's lots of books that are available to you guys in our program. Just because you're students here at Oklahoma State University, we have library resources that are available to you as ebooks. And if you go to the OSU Medical Library and look in pharmacology, you'll find some really good books on this topic if you're interested in reviewing PKPD or pharmacokinetics and pharmacodynamics. So I want to mention all these drugs that we see a lot of drugs out there, and cannabinoids have recently been implicated in runner's high as well, but opioids have long been known to be involved. Endorphins and enkephalins. These are natural endogenous compounds that are going to affect the opiate receptors, and anandamide is an endogenous cannabinoid. So that's like so opioids and opiates, those are what's coming from the poppy plant, and they provide pain-killing effects like morphine. Cannabinoids would be like smoking marijuana. You're going to absorb cannabinoids, and they can have an effect on the acetylcholine system as well. But a lot of these drugs are they're going to interact with these receptors and then these might control dopamine as well. Dopamine is an endogenous neurotransmitter, but these drugs are modifying the release of these endogenous neurotransmitters that give us pleasure. So, or that give us pain, to try and prevent pain. So either way, this is something that you should be aware of. Drugs, the reason they work is because there's receptors in our body that are designed to have these natural occurring biologically produced substances from our bodies work on them, and so we have normal function. And when we take these external drugs, we modify those internal processes, but that's how it works. So I'm going to kind of wrap up a little bit with a couple of case discussions, but I think Tara is going to talk a little bit about that anyway. But in this case, their example is, this is related to workplace drug testing. 41-year-old male applied for a position as an accountant with a large firm. He was provisionally hired pending final approval that awaited the results of a drug test. 3 days later, he was informed that he had failed the drug test because of the presence of methamphetamine in his urine. The offer of employment was withdrawn. The applicant vigorously denied use of any drugs of abuse. Friends attested to his good character, but neither his denials or the testimonials reversed the decision of the employer. Eventually, the applicant hired an attorney and brought suit against the laboratory and the company. Is it possible that there was a laboratory error here? And if the methamphetamine finding was incorrect, how could such an error be avoided? And what aspects of the subject's health history should have been provided to the laboratory? So, well, it turns out that the man had had a severe head cold 2 days prior to the drug test and treated his symptoms with Vicks inhaler, which permitted him to breathe more easily. At the time of the specimen collection for the drug test, he was asked whether he took any medications. He did not mention the inhaler because he assumed that the use of the over-the-counter product was irrelevant. The laboratory found a positive result for amphetamine compounds in screening. GCMS confirmed a positive results for meth. The active agent in Vicks or these similar inhalers is L-methamphetamine, although they sometimes write it differently, but it's L-meth, which is an optical isomer of D-meth. And the inhaler ingredient is a decongestant, whereas D-meth is the illicit abused drug. The compounds are similar and they're not differentiated by customary GCMS or LCMS. During the discovery phase of the case, the litigant acknowledged that he had failed to state that he used the inhaler. The laboratory admitted that its method of analysis could not distinguish between the two drugs. The case was dropped and the applicant was offered the position. This suit could have been avoided by a review of the entire case by an MRO or medical review officer, or by testing of all positives by a more specific GCMS method. Most these steps are currently employed by laboratories certified by the NLCP. So I guess the point is, and it's true for everything else, you need to know what your forensic toxicology results, what your toxicology testing results say, and what they don't say. So a lot of times a methamphetamine positive just means you detected meth. You're not differentiating between the L and the D. And so in this case, he had a reasonable explanation for his L-meth exposure. Recently, there was 2 years ago, an actress died, fairly popular young actress, and she had meth in her system, but it turned out it was actually L-meth, because she basically had a toxic house, and she had lung inflammation, and she couldn't breathe, and she had nasal decongestion or nasal congestion. So she was using a lot of these nasal inhalers. So anyway, it's just something to think about. In that case, she wasn't falsely accused of methamphetamine abuse post-mortem. They determined exactly what it was by the more accurate testing. So let's talk about this next case, this mysterious death. 32-year-old man went fishing with friends. He suddenly collapsed and complained of dizziness and nausea. He lapsed into a coma and medical assistance was summoned. His respirations became very weak. He became cyanotic and eventually suffered a cardiac arrest from which he could not be resuscitated. An autopsy revealed no signs of trauma or evidence of any disease condition. The case was referred to a laboratory that found the fentanyl in the blood of the decedent was about 15 nanograms per mil. And the question is, what was the cause and manner of death? In the absence of any other findings in view of the concentration of the fentanyl found, fentanyl was ruled to be the cause of death. This is a little bit interesting, okay? So we have books that kind of tell us historically what levels of drugs are toxic and or fatal. But it really depends on the individual, and we rely heavily on hypotheticals. But in this case, you can go to the literature, and like in Basalt and Cravey, and they found 12 nanograms per mil could cause death. Looking at his work history, revealed that he was a known drug abuser, and he had recently handled the body of a cancer patient, and 2 fentanyl patches on her corpse at the time of her funeral were missing and presumed stolen by the worker. And one of the things that these people can do with these fentanyl patches, and actually someone did in a murder case in Southern California, if you look up Rossum, you'll find that. But you can extract the drug from the patches and then inject it to get high. But fentanyl is much more highly active than other opiates, and it can be very dangerous. So the manner of death in this case was ruled an accident. So toxicology contributed to this finding, that basically the toxicologist said that this level could have resulted in a fatality, and then the coroner determines the cause and manner, or the medical examiner. So these findings are they're challenging, because there are other things that could be going on in each of these cases, and you really don't know what the specific cause was. But in this case, they did rule it was an overdose. So that's it for your intro to tox. I've given you a few quiz questions about toxicology in general. Gone over quite a bit of history and practice. And I know a lot of the areas, I didn't go over each instrumentation type and how it's run and how it functions. And that's really something we do in the forensic tox class. But hopefully we've given you enough of a flavor of toxicology that it's difficult to do, and we have to be real careful what we say and how our statements are interpreted. Have a great night.